Last couple of days we've been going over. Yes, we are, but I want to just review something quickly here. Okay, last couple of days we have been going over work energy theorem. Now, I didn't think we were ready for that. This is why I read it. I didn't think we were ready for that on the quiz yet. Okay, but the quiz involved some friction stuff, so I wanted to make sure we went over the Newton thing before I did the quiz. So there's no work energy theorem stuff on the quiz. I just say that because I had some people who were trying to solve one of the questions using work energy theorem. Okay, there's no work energy theorem on the quiz. Okay, we'll talk about that in a few minutes. Okay, so if you can get your quiz materials out now, we'll have you guys do that. Okay. Yeah. Okay, so we're going to look quickly here, guys, at a couple of work energy theorem kind of problems, but a little simpler than what we did yesterday with like the inclined planes and things like that. Okay, just going to go over one that's more of a real world application. Okay, so what are some determining factors in how long it takes you, how far you would travel after you slam on the brakes for your car to stop? Okay, how much friction there is? What else? Mass of your car. How fast you're going. Yeah, that's a big one. Okay. Inclined planes. If there's any incline, yeah, if it's uphill or downhill. Okay, all of those things can affect how far you travel before you come to a stop. So, I want you to consider something. Okay, because you guys are kind of new drivers out there. All right. What's the speed limit in a playground or a school? 30 kilometers an hour. Okay, so 30 kilometers per hour is 8.3 meters per second. Okay, 8.3 repeating meters per second. Now, if you're driving through a playground zone or a school zone and you're doing the speed limit, okay, at 8.3 meters per second, you need to, and a kid, let's say, runs out in front of you, you need to convert all of that energy, which is what kind? Kinetic, mechanical and kinetic. Okay, you need to convert that all into other forms of energy in order to stop. What does that? Your brakes. Okay. If you ever watch like racing at night, okay? Yeah, like F1's one, like you can see the brake rotors glow. They're like cherry red inside the wheels. Okay? They're converting mechanical energy into heat. Okay? And in that case, even a little bit of visible light. Okay? And some sound, the screeching and all of that. Okay? All of those are forms of energy that are being produced as a result of converting kinetic energy into other forms and reducing your mechanical energy, thus reducing your speed. Okay? So, stopping is a work energy theorem problem because our brakes are going to do work by changing the kinetic energy of our car. Okay? We want it to go from whatever value it is to what value? 0. Okay? We're trying to stop. We want to go from whatever we have in joules to 0 joules because that means we won't be moving anymore. Okay? So, my brakes use the force of friction to stop. Okay? They're going to do that over a certain distance because that's one of the ways we can calculate work. Is everyone okay with that? Okay. And we're trying to change our kinetic energy. Okay? We want this number to be what? 0. Okay? This number here is completely determined by what kind of car I drive, mass, and how fast I'm driving. Okay? So, if I'm looking at this formula and this is 0, okay, here's what I need to think about from a practical sense, not so much from a physics or mathematical sense. The more mass I have, what will happen to D? It'll get bigger. What about V? Bigger, but not just bigger. Bigger in what way?
Twice.
Not just twice. Exponentially. If I double my speed, okay? So if V is 1, 1 squared is 1. But if V is 2, V squared is 4. If I double my speed, I'm going to have 4 times as much energy to get rid of, which means my car will travel not twice as far, 4 times as far if I double my speed. If I triple my speed, I will go 9 times as far. Okay? It adds up in a hurry because there's an exponential relationship between speed and energy, and thus the amount of work that would be needed in order to take that energy away. Right? So let me do like a quick demo here for you. Let's just say that in this theoretical example, I'm driving a car that has a mass of 1,500 kilograms. Okay? And under ideal conditions, friction can provide 8,000 newtons worth of force. Okay? Just kind of picking up 8,000 newtons worth of friction is available. Okay? I want to calculate how long in meters, so how far, my car will travel before it comes to a stop if I'm going to speed limit in a playground zone. Okay? Do I have enough information to do that? Yes, because I have the force of friction, I have the mass of the vehicle, and I know that the speed limit is 8.3 meters per second. Okay? So if I want to calculate how far I'm going to go, I'm going to leave d over here and do what with force of friction? Divide it over. Okay, so d is going to equal 1/2 mvi squared divided by the force of friction. So that will be 1/2 times 1,500 times 8.3 repeating squared divided by 8,000. Whoops. Okay, so 0.5 times 1,500 times 8.3 squared. Okay, so there's how much energy my 1,500 kilogram car has if I'm going 30 kilometers an hour. Is it still a pretty big number?
Yep.
Yeah, it is. Okay, but I've got a lot of friction. But I'm going to travel 6.5 meters. Okay, 6.5 meters, guys, from the edge of this door right about here. It's almost the length of the classroom. 30? That's going 30 kilometers an hour. Under ideal conditions where I have lots of friction. Okay?
Faulty brakes.
No faulty brakes. It's just a lot of energy. Okay? We got to get rid of that energy, and it takes distance to do that. Now, if I was going twice that speed, how much further would I go? Not twice as far, 4 times as far. Okay? Not 6.5 meters, almost 30. Okay? Is that a lot? It sure as hell is if a little kid runs up in front of you. Yeah. Okay? It's a long, long way. Now, here's the thing. Not many of us are stupid enough to drive through a playground zone when it's active at 60 kilometers. I'm saying not many. I'm not saying everyone. Okay? There are people out there who are that stupid. Okay? But most of us wouldn't do that. But here's what most of us do. Most of us justify to ourselves that it's not a big deal if we go 10 kilometers over the speed limit. Right?
You're right.
I know I'm right. Because I used to do the same thing until I had kids. And then I thought about this and went, oh crap, I'm so not right about that. Okay, and that's what I'm going to show you. Okay, but we justify to ourselves that 10 kilometers an hour doesn't make that big a difference because it's not that much. I'm not really speeding, 40 versus 30, no big deal. Okay, guys, it is a big deal. Okay, it doesn't seem like it is, but 40 kilometers per hour is 11.1 meters per second. Okay, if I do this exact same calculation, but now I put in 11.1 here instead of 8.3. So we have our 0.5 times 1,500 times 11.1 squared divided by 8,000. That distance goes from 6.5 meters to almost 12. it's almost double. It's only 10 kilometers an hour, but because there's an exponential relationship between speed and energy, that little bit of speed ends up meaning nearly double your stopping distance. Okay? Nearly double. Even though you've only increased your speed by about 25%. Okay? What's that? Well, yeah, but they're kids. Kids don't pay attention. Yeah, right. But kids do, right? That's why there's a reduced speed limit in a playground zone, okay, or a school zone, because there's kids around. Okay? Now, guys, here's the thing. We justify that 10 kilometers per hour, okay, all the time in our head. But if I'm looking at an average school zone, okay, a school zone is rarely more than 500 meters in length. Okay, so look at how much time this saves me. Okay, this 10 kilometers per hour. Okay, the time of travel is d over v. Let's say it's a 500 meter long school zone. Okay, at the speed limit, so 500 divided by 8.3. Okay, and it's very rarely is a school zone ever 500. Most of the time they're like 300. Okay. Takes me 60 seconds, 1 minute, at the speed limit. Okay? I saved myself a grand total of 15 seconds by traveling 10 kilometers an hour further and doubling my stopping distance and risking killing somebody for 15 lousy seconds. And the way the lights are timed in Okotoks, you're just going to end up at the red light at the end of the school zone anyway. Okay? You're just going to be sitting there, and the guy who came behind you going the speed limit is going to be right behind you at the light. You're not going to get it. Okay? It's 15 seconds. Just remember that when you choose to do that, what you're saying is this: those 15 seconds are worth more than my kid's life. You're wrong about that, in case you were wondering. Okay? You're wrong about that 15 seconds. Okay? But that 10 kilometers an hour can be the difference between me having dinner with my kid or planning their funeral. Physics is important. It is why there are special speed limits for special places, like schools and playgrounds. Please abide by them. Worse than that, for the love of God, please don't text while you're driving through the freaking playground zone, because that is the epitome of stupidity. I watched a person do that in front of Westmount School a few years ago. They nearly ran down a police officer. Okay? They were going 50 kilometers an hour through the school zone at 3:30 in the afternoon when kids were being let out, and they were texting. The police officer stepped out because he was running a speed trap to pull them over, and they were doing this and nearly ran down the police officer. He had to jump out of the way. Okay? Don't be stupid. That is stupid. Okay? That is, you should lose your license forever because you're too stupid to have one. Okay? That's what that says. Had that police officer been a little kid, they'd have done the deer in the headlights thing, and that would have been the end of it. Okay? So think about it, please. Drive carefully through school zones because of work energy theorem. It's work energy theorem. Okay? That's what it's all about.
You didn't take into account air resistance and stuff, so you'll have to slow down quick.
But air resistance makes very little difference.
It counts!
Okay, it's 2 or 3 centimeters. I'll give you that. Right? At that speed, it's not going to make any difference.
2, 3 centimeters.
Okay, I would like you guys to try a couple of work energy theorem problems from the workbook here. Okay, let's say starting on number 3 here. Okay, so this is on page 6 of the dynamics workbook. Okay, so if you can go to page 6 there, I want you starting on number 3 and working downwards from there on the work energy stuff. Again. Yes.